the Pacific Northwest, one of the most beautiful regions of the United States, home to rugged coastlines, deep forests, cities with character, and stunning mountain peaks and volcanoes. A hub for industry, the Pacific Northwest is the birthplace of several famous staples of American society, from Microsoft to Starbucks. Revered for its beauty, the Pacific Northwest is home to several national parks and countless scenic areas, offering a treasure trove of outdoor recreation activities. Home to 13 million people, the Pacific Northwest is growing, and it's growing fast. But under all of this hustle and bustle lies a ticking time bomb, the Cascadia Subduction Zone. The Cascadia Subduction Zone is a fault line extending just over 600 miles from Cape Mendocino in Northern California through Oregon and Washington to the northern tip of Vancouver Island in British Columbia. Here, the Juan de Fuca Plate dives beneath the North American Plate. This geologic structure is responsible for building all of the iconic landforms in the PNW, from Mount Rainier and Mount Hood to the Puget Sound and the Olympic Peninsula. These landforms, most notably the volcanoes of the Cascades, can give us valuable insight to the geologic history of the area and help forecast the geologic future here. In this special two-part mini-series of Solomon's Outdoor Adventures, we're going to go on a field trip throughout the Pacific Northwest to learn all about its volcanic and seismic past, present, and future. This is episode 1, Volcanoes of the Cascades. In this episode, we're going to learn all about the volcanoes of the Cascades, including how they were formed, past eruptions, future eruptions that could pose a threat to those living in the Pacific Northwest, how to survive a volcanic eruption, and of course, we're going to touch on some rocks that you can find here in the Cascades. So let's go. Part 1. How volcanoes form in the Cascadia Subduction Zone. We begin the show here at Hat Creek Rim Scenic Overlook in beautiful Northern California. We are at the southern end of the Cascadia Subduction Zone, and the big mountain that you can see behind me is the beautiful Mount Shasta. Now, Mount Shasta is an active volcano, and it's the second highest in the Cascade Range, standing at 14,179 feet above sea level. Mount Shasta is beautiful, majestic, stunning, scenic. The list of adjectives regarding Mount Shasta go on and on. Another adjective that can be used to describe Mount Shasta in an accurate fashion is massive. Mount Shasta is the most massive, the most voluminous volcano in the Cascade Range, with a volume of 85 cubic miles, or 350 kilometers cubed. That's a pretty big mountain. So Mount Shasta is really sacred to the local Native American tribes that have traditionally inhabited the area, including the Modoc people. And the Modoc people have a really interesting and cool creation myth regarding Mount Shasta. Modoc culture stipulates that the chief of the sky spirits one day opened a hole in the sky and dumped all of the ice and snow that he could find onto the earth until it piled up into this gigantic mound, this gigantic mountain, that mountain being Mount Shasta. Now, geologists have a different story to the genesis of Mount Shasta, and their story suggests that Mount Shasta was created due to volcanism associated with the Cascadia Subduction Zone. Geologists share the same creation myth for all of the volcanoes in the Cascadia Subduction Zone, but different Native American tribes have different creation myths for each volcano and each sacred mountain within the Cascades. Now, I've mentioned that these volcanoes were formed by the Cascadia Subduction Zone, but what exactly does that mean? What kind of processes and mechanisms went into creating these volcanoes, and why is it important in helping us learn about the past, live in the present, and prepare for the future? We're going to answer all of that right here, and it turns out that one of the biggest reasons why these volcanoes were created is, in fact, water. So let's learn all about that. Water, H2O, Adam's ale. It's got many names, many uses, and is the very chemical that makes Earth unique. Water's role in life is essential. Given our current scientific knowledge, life cannot exist without it. Water is also essential to the formation of the volcanoes of the Cascades. And it's not just Cascade volcanoes. The fundamental geologic process that defines Earth, plate tectonics, is driven by water and would cease to exist without it. In the same way that biological life on Earth cannot exist without water, geological life on Earth also cannot exist without water. But how exactly does water drive plate tectonics, and what is its specific role in forming the Cascades? Let's begin to understand this by discussing the regional geologic processes at play here in the Pacific Northwest. As I'm sure you're already aware of, having gotten this far into the video, a fault line by the name of the Cascadia subduction zone exists off the coast of the Pacific Northwest. At this fault line, two tectonic plates collide, the North American plate and the Juan de Fuca plate. The Juan de Fuca plate is denser than the North American plate due to it being composed of mafic iron-rich rock that is denser than the silicon-rich felsic rock that chiefly comprises the North American plate. Given that the Juan de Fuca plate is denser than the North American plate, the Juan de Fuca plate dives, or subducts, under the North American plate, hence the name subduction zone. As the Juan de Fuca plate forces its way under the North American plate, great amounts of water from the Pacific Ocean get dragged down with the plate, entering the main zone of subduction. The water dragged into the subduction zone from the ocean incorporates itself into iron and magnesium-rich minerals in the Juan de Fuca plate, such as forsterite, transforming or metamorphosing them into hydrous serpentine group minerals in a process known as serpentinization. Additionally, this water lowers the melting point of the subterranean rock near the plate boundary. This melts the solid rock into magma and allows for metasomatism, or chemical alteration of rock, to occur as the iron-rich basaltic magma from the Juan de Fuca plate incorporates water into its chemical structure, changing the chemical composition of this magma. As this metasomatism occurs, iron-rich minerals such as olivine and pyroxene crystallize and exit the melt in a process known as fractional crystallization. The more mafic or iron-rich minerals, such as olivine and pyroxene, crystallize and exit the melt first because they have far higher melting points, roughly 1200 degrees Celsius, than the more felsic or iron-poor minerals such as quartz, which has a melting point of 600 degrees Celsius. As these iron-rich minerals exit the melt loses much of its mass as it is now enriched with lighter, more silicon-rich minerals such as quartz and orthoclase feldspar. Magma that transforms from mafic or basaltic to felsic or rhyolitic is known as evolved magma. It's also important to note that magma that transforms to intermediate or andesitic is also known as evolved. Basically, if it started as basalt and transforms into something else that has more silica, it's known as evolved. Anyways, the evolved magma then rises through the crust to the surface, since it's now buoyant and lighter than the crust, which has incorporated the heavier iron-rich minerals that were fractionally crystallized from the melt. Additionally, assimilation, or partial melting of the existing felsic continental crust, is another key player in evolving the composition of the magma at the Cascadia subduction zone. As this magma erupts at the Earth's surface above the subduction zone, volcanoes are created. In the case of the Cascadia subduction zone, this process has been going on continuously for the last 37 million years. The major volcanoes that we know and love, Mount St. Helens, Mount Hood, Mount Rainier, etc., are far younger, having formed within the last 2 million years. The Cascade Range is home to roughly 3,000 volcanoes, 231 of which have erupted within the last 10,000 years. It's important to note that not every volcano in the Cascades is composed of felsic evolved magma. Much of the magma that erupts from subduction zones is still mafic, and stratovolcanoes such as Mount Hood or Mount Rainier are mainly intermediate in composition. With that being said, the incorporation of water to melt the subterranean rock into magma is what forms the volcanoes, whether the magma ends up evolving into rhyolite or not. Water is the key reason that volcanic arcs such as the Cascades are created, and it's quite poetic how hand-in-hand water is to everything here on Earth, from biology to geology. Now that we've learned about how the volcanoes in the Cascadia subduction zone were formed, let's go see some really cool evidence that just shows how powerful and destructive these volcanoes truly can be. Come on, we're headed towards Crater Lake, a beautiful national park in southern Oregon with a violent past. Part 2. Past Cascade Eruptions. Alright, y'all, we just pulled up to Crater Lake. Check out this beautiful view. So that island that we see there, that's Wizard Island. The little cliff behind it, well, I guess it's a big cliff, that's Lau Rock. And then that pointy mountain way in the back that you see there, zoom into it, that's Mount Thielsen, the eroded remains of a volcano. Now we're gonna just pan across the lake. Look at how placid this lake is. Absolutely stunning. And then that peak right over there, the high one, that's Mount Scott, the highest point in Crater Lake National Park at 8,959 feet. Mount Scott's pretty cool mountain. Climbed it before. Yeah, Crater Lake. Let's just give another panorama. Oh, that is so gorgeous. Look at that lake. Did Justin Timberlake write the song Mirrors about the absolute gorgeous reflectivity of the placid Crater Lake? I think he did. It's like you're my mirror. Oh. I'm here at Discovery Point on the south edge of the lake. Now you might notice I'm not actually standing on the shores of the lake, rather I'm standing on a precipice a few hundred feet above the water. This is because, as the name suggests, Crater Lake is in a crater, and I'm on the southern rim of that crater. Well, technically Crater Lake is in a caldera if you really want to get into the semantics, but I guess Caldera Lake just doesn't roll off the tongue as well as Crater Lake does. This lake is beautiful, and it's really deep. At 1,949 feet, it is the deepest lake in the United States and the seventh deepest in the world. Now, I did mention that Crater Lake has a really violent past. Let's talk about that. The violent geologic history of the area is what created the beautiful lake behind me. Around 8,000 years ago, Crater Lake didn't exist. There was no lake here. This was just a giant mountain, a stratovolcano named Mount Mazama, standing about 12,000 feet above sea level. Mount Mazama has been active for the last 400,000 years, cyclically building itself up and then erupting, blowing its top off. What you see behind me, Crater Lake, this caldera, is the most recent iteration of Mount Mazama's anger issues. 7,700 years ago, Mount Mazama erupted violently, blowing 3,000 feet of its top off and collapsing in on itself, forming the caldera that you see behind me. The last time Mount Mazama was active was 4,800 years ago, when Wizard Island, the island that you see in the lake behind me, last erupted. Mount Mazama is currently considered dormant. There's still a vast reservoir of magma beneath the mountain, and hydrothermal activity persists at the bottom of the lake today. The volcano could erupt tomorrow, and it's considered the 17th most dangerous volcano in the United States out of 169 potentially active ones. Now, we just talked about how the caldera was formed, but how did the lake itself form? Well, over the last 7,700 years, repeated episodes of rain and snow have filled the caldera up with 2,000 feet of water. You know, the Cascades are one of the wetter areas of the United States, and this is really testament to it. Crater Lake has no natural inflows or outflows. No rivers flow into it, and no rivers flow out of it. So this is all created by precipitation. A fun fact that you can see that really shows testament to this is that there are actually no native fish to Crater Lake because they can't swim up here. The cataclysmic eruption of Mount Mazama 7,700 years ago that formed this beautiful caldera behind me really shows how powerful the Cascade volcanoes truly are. If an eruption like that were to occur here tomorrow, life as we know it would be significantly altered, due mainly to the large volumes of ash that would be ejected from the volcano. With that being said though, Mount Mazama is not really located in a highly populated area, so it wouldn't do a lot of immediate damage in terms of casualties, just because there's not a lot of people around here. The same cannot be said for Mount Hood and Mount Rainier, two Cascade volcanoes in close proximity to large urban centers, Portland and Seattle, respectively. Let's go head up to Mount Hood to learn more about future Cascade eruptions and the implications those eruptions could have on society and life in the Pacific Northwest. Part 3: Future Cascade Eruptions. Mount Hood, more like Mount Good, looking whoop whoop. Boo. I'm standing here on the slopes of the majestic Mount Hood. Towering at 11,239 feet above sea level, Mount Hood is the highest mountain in the state of Oregon. As you could have probably guessed by now, it's an active volcano, and Mount Hood poses a significant threat to the cities and communities immediately downstream of it, including over 37,000 people in the cities of Hood River, Sandy, and Troutdale. The specific location on the slopes that I am at on Mount Hood sheds light into the volcanic history of the area. Now, this big boy right here that I just picked up so y'all can see, this is a specimen of andesite, an intermediate volcanic rock. Big boy. Anyways, you might notice that immediately behind me is just a bunch of bare rock surrounded by hills with trees. This area here of bare rock is where a lahar, or volcanic debris flow, flowed and raced down the mountain the last time Mount Hood erupted. This particular lahar deposit that I am standing on dates back to 1781, only 243 years ago. Back in 1781, a lava dome called Crater Rock near the summit of Mount Hood collapsed as the volcano erupted in an event known as the Old Maid eruptions. The hot lava that spewed out of Mount Hood rapidly melted all of the glacial ice and snow in its vicinity, causing a slurry of hot concrete-like material composed of water and molten rock to race down the mountain, particularly into this valley that I'm standing in. This material is what composes a lahar. As you can see, the lahar completely razed everything in its path, and today, nearly 250 years later, trees still do not grow in the path of this lahar. This is exactly what the communities of Sandy, Troutdale, and Hood River are at risk of in the event of a Mount Hood eruption. The lahar that would result from an eruption would take out roads, buildings, houses, cars, and people in its way, things that were not here back in 1781 when Mount Hood last erupted. Now, if you look up for yourself when the last time Mount Hood erupted, you might be a little confused because some sources say it was 1781 and others say it was 1866. The sources that say it was 1866 are citing early settlers' reports of volcanic activity on the mountain. Witnesses saw fire, smoke, rocks, and steaming. But there is actually no geologic evidence that that eruption occurred. The last eruption that we have geologic evidence for occurred in 1781, which is why I cite that as the last time Mount Hood erupted. Though lives would be saved given ample warning to get out of the path of the lahar, property would not be, and the aforementioned towns would be completely at the mercy of Mount Hood. The resulting eruption would cause billions of dollars in damage, and it would likely take years to rebuild the communities immediately downstream of Mount Hood, displacing over 37,000 people. Though Mount Hood is a very dangerous volcano itself, it pales in comparison to the danger imposed by Mount Rainier, which we're going to touch on right now. For the exact reasons that I just outlined regarding Mount Hood and lahars, Mount Rainier is an exceedingly dangerous volcano. An eruption on Mount Rainier would be absolutely cataclysmic, its danger magnified due to its colossal size, gargantuan glacial ice reserve, and proximity to the Seattle-Tacoma metropolitan area. The USGS stipulates that the lives of 795,000 people would be at stake from a lahar alone if Mount Rainier were to significantly erupt tomorrow, putting it on the list of decade volcanoes, 16 of the world's most dangerous volcanoes, as outlined by the International Association of Volcanology and Chemistry of the Earth's Interior. In the past, lahars from Mount Rainier have traveled as far as Renton, over 50 miles away from the volcano. The very fact that one volcano, Mount Rainier, threatens the lives of over 795,000 people is quite alarming. Moreover, there are over a dozen volcanoes not named Mount Rainier in the Cascades that threaten the lives of 7 million people across other communities. From south to north, we have Lassen Peak, Mount Shasta, Medicine Lake Volcano, Mount Mazama, Newberry Volcano, the Sisters, Mount Jefferson, Mount Hood, Mount St. Helens, Mount Adams, Mount Rainier, Glacier Peak, Mount Baker, and Mount Garibaldi. Of these volcanoes, the 5 most likely to erupt in the near future are Mount St. Helens, Mount Hood, Mount Baker, Glacier Peak, and Mount Rainier. With that being said, all of these volcanoes have experienced and showcased volcanic activity within the recent past, and any one of them could blow tomorrow. The science of forecasting when exactly a volcano will erupt is non-existent. We cannot predict when exactly a volcano will erupt. We can look at past eruptions and past volcanic activity, come up with patterns, and then come up with a likelihood of when the volcano will erupt within a time frame, but we can't exactly predict when a volcano will erupt. So any one of these Cascade volcanoes could blow tomorrow. Though this might all sound frightening, there's actually a lot that you can do to ensure your survival in the event of a volcanic eruption. Let's head on down to Powell Butte in Portland to talk all about that. Spoiler alert, Powell Butte offers stunning views of one particular volcano that infamously blew in 1980. Part 4: Surviving a Volcanic Eruption. I'm here at Powell Butte State Park in beautiful Portland, Oregon. The volcano we're looking at now is the infamous Mount St. Helens, the most active volcano in the Cascades, and the volcano ubiquitously known about for violently erupting in 1980. Though it blew in 1980, Mount St. Helens actually last erupted in 2008, as it's going through a period of rebuilding itself. Mount St. Helens is the most likely volcano to erupt again in the Cascades, and it's almost certain that it will erupt within the next 50 years. With that being said, Powell Butte offers the perfect vantage point to learn all about how to survive an eruption here in the Cascades. The Pacific Northwest is volcano country, and if you live in the PNW, knowing how to survive a volcanic eruption is a must. The good news is, volcanoes in the Cascades are some of the most heavily monitored volcanoes in the world, and unlike earthquakes, volcanoes tend to give us some semblance of warning before they blow. Before an impending eruption, volcanoes tend to wake up, outputting more volcanic gas, hosting swarms of earthquakes as magma moves underground, and even visibly bulging and deforming as magma rises from the subterranean magma chamber towards the surface of the volcano. Since the Cascades are so heavily monitored, geologists are able to detect these changes in real time and notify the public immediately. Start your preparation out by familiarizing yourself with where you live. There are tons of maps online that will tell you if you are in the path of a potential lahar from a volcano. Western Oregon University has volcano hazard maps online for various Cascade volcanoes, which I'll link in the description. Seattle.gov and Oregon.gov also have volcano hazard maps for the public to peruse. Familiarize yourself with your surroundings and prepare a bug-out kit. Stockpile food, water, warm clothing, entertainment, and first aid supplies, among other things. Additionally, I would stockpile N95 masks. In the event of ashfall from a volcanic eruption, the very act of breathing can be deadly. Tiny particles of ash and volcanic debris as small as 10 microns can absolutely damage your lungs, since they're literally tiny crystals. That's crystals in your lungs. N95 masks filter out particles as small as 0.3 microns, so they will protect you from breathing in ash. If you don't have N95 masks, you can also use a wet shirt or wet towel to filter out particles, though that isn't as effective as an N95 mask is. If you live in the path of a lahar and a volcanic eruption is imminent, evacuate immediately. The last and perhaps most important thing to remember when it comes to surviving a volcanic eruption is to not panic. I know it's easier said than done, but keeping a cool head is paramount to survival. If you make the necessary preparations, you'll be absolutely fine, and the authorities are there to help you in the event of a natural disaster. Keep calm and try to make the best out of whatever situation you find yourself in. Now that we've learned how to survive a volcanic eruption, let's make one final stop to talk about some rocks. Come on, we're headed down to Newberry National Volcanic Monument just outside of Bend to briefly discuss the three main types of rocks that you can find here in the Cascades. Part 5: Volcanic Rocks of the Cascades. I'm at Newberry National Volcanic Monument just outside of Bend, Oregon. I'm here at the Trail of Molten Land, and this lava flow that I am standing on is actually really young geologically speaking. It's only 7,000 years old. A long time for humans, but the blink of an eye geologically. So let's dive into some of the rocks, shall we? This rock is known as basalt. Now, basalt is derived from mafic magma, which we learned about. Mafic magma is high in iron and low in silica. Basalt is an extrusive igneous rock, or a volcanic rock, meaning that basalt is formed as lava erupts out of a volcano and cools at the surface. So basalt is quite common in the Cascades. You can find it here on the Trail of Molten Land in Newberry National Volcanic Monument, and it's also common throughout much of the rest of the Cascades. So basalt, mafic, volcanic rock. And the common minerals that you can find in basalt include olivine, pyroxene, amphibole, and plagioclase feldspar. The entire lava flow that I'm standing on, that you can see all around me, is composed of basalt and erupted out of that cinder cone 7,000 years ago. Now, the next volcanic rock that we have here in the Cascades is known as andesite. Andesite is derived from intermediate magma, meaning it's about 50-50 in iron and silica content. Now, we kind of touched on andesite a little bit earlier on in the video when we talked about future volcanic hazards and eruptions at Mount Hood, and that's because Mount Hood and pretty much all of the other stratovolcanoes in the Cascades are composed of andesite. Some common minerals in andesite include plagioclase feldspar, quartz, biotite mica, and hornblende. This is why andesite is kind of gray in color. You have some of the lighter minerals, and you also have some of the darker minerals. Now, the last main volcanic rock that we have here in the Cascades is rhyolite. Rhyolite is derived from felsic magma, magma that is rich in silica but low in iron. Rhyolite is the most evolved of the volcanic rocks and is commonly found in lava domes on some of the Cascade summits, such as Mount St. Helens and Mount Rainier. Rhyolite is mainly composed of potassium feldspar, quartz, and muscovite mica. And rhyolite is pretty light, both in color and in weight, because it is enriched in silica and depleted in iron. So yeah, those are the three main volcanic rocks that you can find here in the Cascades. The Cascadia subduction zone has been active for the last 37 million years and will continue its activity for millions more to come. The volcanoes of the Cascades document the geological processes at play in the Pacific Northwest beautifully. They've constructed the very foundation of this landscape and life in it, while simultaneously being responsible for some of the death and destruction here. The life of a volcano is perhaps more similar to the life of a human than meets the eye. We both require water to live, we both document our histories, and we both simultaneously build and destroy society. In these past 25 minutes, we've journeyed together to learn all about the volcanoes of the Pacific Northwest, and though we've learned a lot, we've merely scratched the surface in understanding them. As is true in all facets of life, there's still much to learn, and I hope that you learned at least a little bit about the Cascade volcanoes in this video. Moreover, I hope you enjoyed it. Thank you for watching this special episode of Solomon's Outdoor Adventures, and be sure to stay tuned for episode 2 of this mini-series. In episode 2, we're going to learn all about the infamous Big One, the gigantic megathrust earthquake that is primed to hit the Pacific Northwest. You're not going to want to miss that. Thanks for watching, and peace! Thank you for tuning in to another episode of Solomon's Outdoor Adventures. If you enjoy content like this, please like the video and subscribe to the channel, and check out some of our other adventures right here. As always, guys, thanks again, and peace!